Good afternoon, everyone, and welcome to Teledyne Tekmar's webinar on the analysis of Geosmin and 2-Methylisborneol utilizing Purge and Trap with GCMS. My name is Tammy Reller, and I am an application specialist. I spend quite a bit of my time in the field and have visited many of you recently that I see on this list. In today's webinar, we're going to take a look at the overview of some of these off-odor or taste and odor compounds. We're going to look at current methodologies that are used for this particular analysis. We're going to look at the analysis of Geosmin and 2-Methylisborneol, and from now on I will refer to that as 2-MIB, at a 1 part per trillion level using Purge and Trap with GCMS. Now, when we were doing this study, we decided to look at 3 different techniques of using Purge and Trap. And we looked at a comparison of cryofocusing, where we used liquid nitrogen at -100 degrees Celsius temperatures to concentrate the band of analytes at the injection port. We also looked at a splitless injection technique, and we also looked at direct column injection, where we took the transfer line from the Purge and Trap concentrator and connected it directly to the column, so that you get essentially all transfer of analytes directly onto that column. We looked at each of these techniques with regard to linearity, method detection limits, or MDLs, precision, accuracy, and percent carryover. Now, Geosmin is produced by several classes of microbes, including cyanobacteria, blue-green algae, and actinobacteria, especially the streptomyces, and is released when these microbes die. Now, communities whose water supply depends on surface water can periodically experience episodes of unpleasant tasting water when a sharp drop in the population of these microbes releases Geosmin into that local water supply. Now, Geosmin is also responsible for that earthy taste of beets and contributes to that strong scent that occurs in the air when rain falls and after a dry spell of weather. Now, cyanobacteria produce Geosmin and 2-MIB, which can also concentrate in the skin and dark muscle tissue of some bottom-dwelling fish, such as carp and catfish. Now, these compounds break down in acidic conditions, so when you're cooking or cooking some type of fish or things like that, if you're adding vinegar or any other acidic ingredients, it helps to cut down on that muddy flavor that you might have when it comes to cooking and the taste of fish. Although these compounds haven't been shown to cause any serious health problems, nonetheless, in today's environment and the ongoing push for ultra-clean drinking water, these compounds must be removed. I mean, after all, who wants to drink something that smells like mold? If we take a look at the molecular structures of these 2 compounds, all we're trying to show in this slide is that these are 2 very, very large compounds. So when we're looking at things such as sample size and the analytical trap, we need to make sure that we choose the appropriate sorbent material in the trap so that we can easily trap these compounds, but we must be able to readily get them or desorb them back off of that analytical trap. Otherwise, we could run into some issues with carryover. A survey conducted in more than 800 utilities in the U.S. and Canada had found that about 16% of the utilities experienced serious taste and odor problems. And this study was done in 1996. I haven't been able to find anything more recent, so I'm sure that number has increased quite a bit. And that some of these utilities spend an average of about 4.5% of their total budget on the taste and odor control. And basically that means they're spending that money to minimize those microbes. Some of the challenges we face are that the odor threshold for these compounds is very, very low and can be detected in drinking waters by most of us at around 5 to 10 nanograms per liter, or 5 to 10 parts per trillion. Many drinking water facilities are now requiring detection levels of below 10 parts per trillion. If we take a look at some of the current techniques today, the first one I'm going to talk a little bit about and touch briefly on each one of these techniques and then go into a little bit more detail with regard to the Purge and Trap. The first one is a closed loop stripping analysis, or CLSA. that is found in standard method 6040B. Solid phase microextraction, or SPME as most of us know it, is found in standard method 6040D. The stir bar sorptive extraction method, and of course our purge and trap method with GCMS, is found in the standard method 6040C. If we take a look at closed stripping analysis, it's basically a dynamic headspace technique that's coupled with sorption onto activated carbon or charcoal and uses solvent desorption to remove those analytes back off. These analytes move from that liquid phase, generally the water, into the gaseous phase, and then they're collected onto the activated carbon or charcoal filter. Then a suitable solvent is used to extract those analytes from the carbon and into the GC. For SPME, or solid phase microextraction, this technique uses a syringe-like device surrounding a coated fiber of DVB, which is divinylbenzene, carboxin, and polydimethyl silicone. The fiber is exposed to a gas or liquid phase for a period of time. That time, just depending upon the range of the analytes that we are looking at, can be anywhere from maybe 20 minutes to 120 minutes. It depends on how long those analytes take to absorb or adhere to that coated fiber. And picking those fibers is similar to picking the type of trap. You want to make sure that they have an affinity for those analytes so that it will hold on to the analytes until they're ready to be desorbed. So it works very similar to an adsorbent trap. The syringe then moves to the injection port, and a plunger exposes that fiber to heat and then thermally desorbs those analytes off of the coated fiber, and usually that takes around 4 minutes or so. The stir bar sorptive extraction uses a magnetic stir bar incorporated into a glass jacket coated with a 0.5 millimeter layer of polydimethylsiloxane. Then the extraction is performed by placing a sample amount in a vial. Usually they're using, say, 22 mil headspace vials, and put about 10 mil sample into that vial. And that's often the case with SPME as well. With solid phase microextraction, you can put the fiber, the coated fiber, either into the gas phase and let the analytes adhere that way, or you can extend the fiber all the way into the liquid phase. With this is a little stir bar that's actually put into the liquid, and then stirring occurs for about 30 to 120 minutes. Once again, depending upon your type of analytes and depending upon the type of sorbent material that's incorporated into that glass jacket. Once the extraction process is finished, we're then going to take that stir bar and introduce it into a glass desorption tube and place it into a thermal desorption unit. Now we're looking at purge and trap analysis. Volatile compounds are purged from the matrix, usually waters, soils, wastewaters, depending upon what you're looking at, into the headspace above the sample and collected onto an adsorbent trap. After that purging process is complete, which usually takes around 11 minutes for your average range of analytes, let's say from anything from dichloromethane all the way out to your naphthalenes. The trap is rapidly heated and then backflushed with carrier gas to desorb, and it transfers the analytes over to the GC or GCMS spec. Now, if we look at this plumbing diagram here, we can see that the carrier gas comes in the inlet to the back of the unit and travels through a sample pathway, and we're going to come, and it's going to bubble up through the sparge vessel, and those analytes are going to come over and collect on, they're going to go through the condensate trap. And the idea behind the condensate trap is that the analytes are purged at a lower temperature, usually around 20 degrees, and the analytes, the water will drop out into the bottom of the condensate trap, and the analytes will pass over the top of that and continue on through the adsorbent trap where they're caught there. Now for this analysis, for the Purge and Trap, for the GCMS, we used an Agilent 7890 5975C with a 1 millimeter ID inlet split liner, and we used a J&W DBVRX 30 meter 0.25 1.4 micron film thickness column. And we used these parameters for all three techniques that we were looking at. The oven program, we started at 40 degrees Celsius and held that for 2 minutes, ramped 16 degrees a minute to 160 degrees. Then we ramped 20 degrees a minute to 240 degrees and held that for 5 minutes for a total runtime of 18.5 minutes. We kept the inlet at 220 degrees Celsius. The pressure was at 12.09 psi with a column flow of 1.02 mils a minute using helium carrier gas. The MS conditions, we kept the source at 230 degrees, the quad at 150. We had a 5-minute solvent delay. All analyses were done in selective ion monitoring, so we used SIM ions 95, 107, 108, 112, 125, and 126 with a 100 millisecond dwell time per ion. For the Purge and Trap, we used our Stratum Purge and Trap concentrator with the Aquatech 70 auto sampler, a 25 mil Teflon sample loop, and a #1 analytical trap. Now, a 10x trap is used for this analysis because these are big compounds. If the sorbent is too strong, then it will be difficult to get the high molecular weight compounds like Geosmin and 2-MIB to desorb back off the trap, not to mention the issue of potential carryover. When choosing an analytical trap, it must retain the analytes while allowing oxygen and water to pass through. Upon heating, it must be able to release the analytes quickly and efficiently. It must be stable and not contribute to any excess background or cause any types of catalytic reactions. So we kept all the GCMS parameters the same, and these are primarily the parameters that we changed within the techniques that we use. So for the first technique, I said we looked at a cryofocusing module where we used liquid nitrogen. So the analytes are purged onto a #1 10x adsorbent trap. Once they are collected onto that trap is then heated and back flushed for desorption and goes over and is stopped with the -100 degrees liquid nitrogen. And they are collected in a band there. The whole idea behind cryofocusing is that the analytes are supposed to collect in a more tight band, improving the sensitivity. And originally, when we started this project, we thought that cryofocusing was the only way that we were going to be able to get down to the 1 part per trillion levels. And then we decided, once we looked at it and we started to see some of the results, that's when we moved forward and said, all right, let's try these other 2 techniques as well and see what kind of response we can get. So the next technique we looked at was a split ratio of 10:1, where we took the transfer line coming from the back of the Purge and Trap concentrator and connected it directly to the side of the injection port and set up a 10:1 split ratio within the GC. And last but not least, we used technique number 3. We did a direct column connection where we take the transfer line and bypass the inlet of the injection port and directly connect it to the column so that you get essentially 100% transfer of analytes on to the column. For calibration, we made up a 50 ppb working stock standard, and we used 5 microliters of that Geosmin and 2-MIB standard into 10 mL of methanol, and that gave us our 50 ppb working standard. Our calibration range was 1 to 100 part per trillion. And then in order to make those calibration range, we prepared those in a 50 ml volumetric flask filled to volume with 10% weight volume sodium chloride and deionized water. Now, sodium chloride is often used to help lower the partition coefficients of some compounds, improving the purge efficiency of certain analytes. A lot of times you will see this in static headspace analysis. In static headspace, there are a lot of things that are going on when those analytes are trying to reach equilibrium. And anything that we can do to help move those analytes out of the matrix and into the headspace faster is different ways of altering those partition coefficients. Sometimes you can do it with heat. Sometimes you can do it with pH. One of the ways to do it is also with sodium chloride, because it starts to reduce that hydrogen bonding and allows those analytes to get into the headspace more readily. Now, the statistical analysis, or the validation criteria that we looked at the linear regression in the percent RSDs for the calibration curve for both compounds. Method detection limits were determined by analyzing 7 replicate standards at a 1 part per trillion concentration. We also looked at the precision and accuracy, in which we analyzed another 7 replicate standards at 10 part per trillion, or what we call the mid-calibration level. In order to check the percent carryover regarding this study, we ran 3 consecutive blanks after the 100 part per trillion calibration standard. So let's first take a look at technique number 1, the cryofocusing module. The parameters to really focus on in this method are to look at the condenser purge temperature, which was set at 20 degrees, and that's where we're purging through the sample, we're purging the sample matrix, and that is going to pass through the condenser and condense out the water so the analytes can go and pass over the top of that. Initially, we started with a purge time of 12 minutes and a desorb time of 6 minutes. And this was because we needed some starting times, and as you see, as we get through the next couple of techniques, we have improved on those purge time and the desorb time. As we saw the results and we were able to measure the responses, we were able to shorten those times, because we all know that we have to get the maximum amount of samples through in as little amount of time. So we tried to, as we worked through each of these techniques, we tried to optimize the parameters as we went. You can also see that the focusing temperature over on the right-hand side, about 5 or 6 down, is minus 100 degrees Celsius. If we look at a chromatogram here, 50 parts per trillion with the cryofocusing module, we can look, it's a little light to see, but we can look and see that we're getting an average area response of about 225 to 250,000 with each of the compounds. Looking at the linear regression, it was 1.0 for each of these compounds. The percent RSD for the calibration curve was 3.94% for Geosmin and 6.52% for MIB. This table is a summary of the linearity, method detection limits, and the precision and accuracy. The calibration curve linearity, as we mentioned in the previous slide, was 1. We ran the MDLs, as I said, 7 replicates at 1 part per trillion, and the MDL for Geosmin was 0.114, and for 2 MIB was 0.236. The precision, the percent RSD for those 7 samples was 5.8% and 7.4% respectively. And the percent recovery for both the analytes was around 104 and 107%. So very good overall analysis for the cryofocusing. We also looked at the percent carryover, and the first blank after a 100 part per trillion standard showed a 0.12% carryover and 0.09% for 2 MIB. So very, very minimal carryover whatsoever. The next technique is looking at using a split ratio of 10 to 1. If you compare this to the first set of purge and trap parameters, you will see that we've now taken the purge time from 12 minutes down to 10 minutes, and the desorb time from 6 minutes down to 2 minutes. We found that that was efficient enough to get enough analytes over to the analytical column. We do have a very low split at this point at 10 to 1. We take a look at the chromatogram, 50 part per trillion at a 10 to 1 split. If we look at the area counts, we can see they're quite a bit lower, as we would expect, because we're splitting off 10% of the sample. The area counts went from about 225,000 with the cryofocusing down to about 140,000 or so. I wanted to show the electron ion chromatogram, the EIC for the 10 to 1 split, to just show how the integration was done on these particular compounds. And here it is for the 2 MIB at 1 part per trillion. Now, as you can see, when you're getting down to levels that low, the chromatography is not exactly beautiful, but we are still able to get 1, 2, 3, 4, 5, at least 5 or 6 scans across the peak in a good integration. Here we have the linear regression for both those compounds at 1 as well. And Geosmin showed a percent RSD for that calibration curve at 3.99%, and 2 MIB was at 1.7%. So our calibrations for these, looking at 1 to 100 part per trillion, are very linear. If this, we are looking at a table right now, and this is for the 10 to 1 split. If we look at the MDLs, they're about the same, maybe just a little bit different than the cryofocusing. For Geosmin, the MDL, method detection limit, was 0.123, and for 2 MIB, it was 0.206. The percent RSDs were 3.6 and 4.25, respectively, and you can see we looked at the percent recovery of the analytes out of that sparge vessel. The percent carryover for the 10 to 1 split was around 0.44% for the first blank, and then the remaining 2 blanks after that were 0 carryover whatsoever. So once again, we are able, and this is what I was talking about earlier, if we were to use a type of trap that has different sorbent beds or stronger sorbents in them for these 2 types of compounds, we may be able to trap those compounds onto that sorbent material, but we may not be able to get those compounds back off of that sorbent material. So that's why 10X has proven to be a very good sorbent for this study. It can trap the analytes, but it can also desorb them off so that we don't continue to see them in our following samples. The last technique we're going to look at is the direct column connect. We used exactly the same parameters that were used into the 10 to 1 split. We had a purge time of 10 minutes and a desorb time of 2 minutes. Now looking at these area counts, you can see with the direct column connection, you are transferring almost all of that sample that's coming off the sorbent trap directly onto the analytical column. You're not splitting any of it off. And the area counts have now gone back up and increased into about 425 to 450,000. So as far as overall response, the direct column technique gives us the best results. Looking at the linear regression, we have a 1.0 curve again. The percent RSDs were 7.18% and 7.35% for 2 MIB. Looking at the table, our MDLs for Geosmin were 0.220 and 0.172 for 2 MIB. And in each one of these techniques, the MDLs have turned out to be very similar in nature. So in cryofocusing, I think for Geosmin it was 0.114, and for the 10 to 1 split, I think it was 0.123, and now we're looking at 0.220. So each one of these is one of the techniques. It's more preference, although we can definitely tell that we have increased the area counts, the overall area counts, using the direct column connect. The percent carryover, once again, we've shown that due to the desorption characteristics of the 10X, we were able to get all that compound off. We only had 0.11% or 0.04% for 2-MIB carryover with nothing in the following blanks. In conclusion, the purge and trap performed well using all three of these techniques. The linearity for all curves was 1 for both compounds with a percent RSD below 10%. The system displayed excellent precision and accuracy. The detection limits for the compounds were below 0.25 part per trillion for all three injections for the cryofocusing, the 10-to-1 split, and the direct column connect. A 25 ml sample volume and a 10% weight per volume solution helped to increase the purge efficiency and by lowering the partition coefficient. Further analysis of the compound responses for all three techniques revealed that the direct column configuration had the optimum compound response. As if we can remember back, we had an area response of about 425 to 450,000 for the direct column. We had about only 140,000 for the 10-to-1 split, and about 225 to 250,000 for the cryofocusing module. Now this is completely automated. We're not having to deal with any messy solvents, no expensive fibers. We have short extraction and desorption times. Originally, in some of the earlier techniques that we talked about that are currently being used, you have long extraction times, anywhere from 30 minutes to 120 minutes. You may have fibers or filters that have to be conditioned before and after each one of those. Or you may be using excessive amounts of solvents to get those. All these things add into the cost of this overall analysis. This you're able to use, many of you are already using purge and trap in your laboratories, running 500 series methods, 600 series. The difference is you wouldn't be able to run those concurrently because you are using different traps. For 500 series, most of you are using either a number 9 trap or some type of Vocarb 3000, so you would have to be able to swap the traps back and forth or have a separate purge and trap system completely dedicated. So the only additional cost that you have other than a regular purge and trap system is using a 10x trap, and so you don't have any additional consumables to buy in order to perform this analysis. I want to thank you very, very much for your time and interest in the webinar we presented here today. I know we've kind of gone through an overview on this, and we had to do this project rather quickly for a client of ours. And it is being used quite a bit. As a matter of fact, in Japan, it's being used a lot by Purge and Trap for doing this analysis. And if you have any other questions regarding this or Headspace or any other applications, please feel free to email me at treller@teledyne.com. And also, you can go in and download a copy of this application note at www.teledynetechmar.com. Thank you so much.